Let's do some rigid body kinematics. We ended last time. We introduced the Euler angles and considered the Euler angles are a way to represent that rotation matrix. When you've got a rigid body, let's put it arbitrarily oriented in space. There's the rigid body, and you've got a frame attached to the rigid body, the B frame. And once we eventually get to rigid body dynamics, we'll be talking about how the angular velocity vector changes with time according to the dynamics. And we want to know how, as the angular velocity changes, how does that change the orientation of the B frame or the B unit vectors, the triad of unit vectors that describe the body fixed frame? How do those move? Meaning, how does the rigid body move as compared to the inertial frame directions? And all of that is contained in that rotation matrix C, which will be, in general, changing in time. And then using the explicit frame labeling, right? The C matrix represents how the B unit vectors are moving compared to the N unit vectors. So this changes. The body is going to be arbitrarily rotating around according to the angular velocity is. And that'll usually be due to rigid body dynamics. And when we get into trying to control, when you want to control your spacecraft, you often want to keep the orientation at some fixed orientation, or maybe it's sort of slightly turning to look at something or get an instrument pointed somewhere. Now this matrix C, like we've talked about, it's a rotation matrix. It's an orthogonal matrix. It has 9 entries. You can write the matrix ODE, right? You take that omega vector, and this is omega, we usually think of omega written in the B frame. So it's the B frame components. It's often written as the body fixed angular velocity, which is kind of confusing. What we mean is the angular velocity, but written with respect to these B frame components. You take that vector, you do that tilde operation that we've talked about a bunch, where you turn the 3 entries, omega 1, omega 2, omega 3, into this skew symmetric matrix, and then that'll be times C. So this is the kind of fundamental kinematic differential equation for how the rotation is changing. But because it has 9 parameters, it's a bit unwieldy to work with. So we decided, let's try these Euler angles. Euler concluded that, well, you could represent any orientation as a sequence of 3 pure rotations, and then you do this matrix multiplication. So then you can get an Euler angle set. So instead of, this is 9 scalar ODEs that describe how the orientation changes. The Euler angle sets are 3 parameters. Last time we talked about the kinematic differential equation written in terms of Euler angles. B, I don't know why they call it B, has nothing to do with body fix. It's just a B matrix. And you look those up in the appendix for whichever is the appropriate set of Euler angles, because remember, there are 12. The common one we use is the 3-2-1 Euler angles, written in the way it's described in this book, or ZYX is another convention you'll see. And this was all times the omega vector written in the body fixed frame. So this is simpler because this is only 3 scalar ODEs. They're nonlinear. Up here, this was linear. So it's a bit easier to deal with nonlinear. Well, I guess it's a trade-off. Would you rather have 9 linear ODEs or 3 nonlinear? Well, these have another drawback, which is that at some angles, they have a singularity, meaning at some angles, this matrix B becomes infinite. So at certain Euler angles, this kinematic differential equation has a singularity. I mean, and that means numerically, your algorithm just stops. It can't handle infinite things. You'll get an error, and we don't want that. So at the very end, last time, we mentioned another set, again due to Euler, and this is the axis and angle way of writing a rotation. So the axis angle way of writing a rotation. And we'll eventually get to that. I think we wrote the axis as E and the angle as a capital phi. And I'll describe what those are. Eventually, we'll get to some ODEs about how those change in time. These are sometimes called the principal axis and angle of rotation, or Euler's axis and angle of rotation. You just got to know. Some people use different words. Some people use different symbols. So the idea here is that if we had the two frames lined up initially, so there's the n frame, right? The n directions, n1, n2, n3. It's a right-handed coordinate system there. And the B frame, and they're lined up to do any rotation. So there's the n directions, and then the B directions are pointed somewhere else now. N2, N3. So any arbitrary rotation can be written as a pure rotation about an axis with unit vector e hat through an angle capital phi. What do I mean by pure rotation? This means there's some special direction, and it could be calculated, and we'll write that as e, going through some angle capital phi. So pure rotation means we're not doing a sequence of 3 rotations. There's some special orange direction. You could go from the initial configuration here on the left where the frames are aligned to where the B frame is at the end by doing just a rotation about that one direction. So that can be powerful, and you can calculate these. So you can calculate these based on the C matrix, so that you can go from the C matrix to this set, the axis and angle, and vice versa. Or if you wanted to go from Euler angles to that set, the usual route is you, from the Euler angles, knowing which set you've got, let's say it's yaw, pitch, and roll, then you would construct the C matrix and then figure out what A and E are. And I couldn't find examples online, so I made them. So I'm going to show some animations that show the space shuttle. This is one of my space shuttles. So there's the space shuttle. Imagine just, we've got the space shuttle initially pointed this way, and then we're going to turn 90 degrees to the left. Well, that one's pretty easy. It means there's an axis pointing up. So I'll show an orange arrow. That would be our axis of rotation. That would be E hat here. And we'd be doing an angle of 90 degrees, or pi over 2 written in radians. Yeah, here it is. So what I'm showing here is in red, that's the initial configuration of the space shuttle aligned with the red frame. And then blue is the final one. And that orange vector is showing the Euler axis of rotation. And this is a movie that shows the rotation going from one configuration to the other, pure rotation. Now that one is kind of easy. So for 90-degree turn to the left, the axis and angle are kind of obvious. What about something not so obvious? So if I did a yaw, pitch, and roll of negative 90 degrees, so that would be a yaw of negative 90 degrees is still 90-degree turn to the left, but then a pitch of 30 degrees, and then a roll of 30 degrees. So that now turns this that. Now it's not so obvious, what's the axis and angle. So this is showing the red is the initial, and then blue is the final. And there's some axis, you can see where it is in orange. And then here we are kind of smoothly. This is a pure rotation about that direction, taking us from one orientation to the other. And then I'm just sort of scrolling around here so you could see. Maybe we could see that again. Ooh. Nice smooth rotation. Okay, that's enough of you. We can go from C to, looking up here again, we can go from C to this axis and angle, and maybe we could even try that. Eventually we'll try it for an example. You could find this in, I think it's section 3.5 for, I'll just give you the upshot. We first write the angle to get the angle from C. This is it. The angle is, we could write inverse cosine or arc cosine. I'll write inverse cosine of 1/2. I'll write it this way in terms of components. C11 plus C22 plus C33 minus 1. And if you notice what this is just trace of that matrix, right? The sum of the diagonal elements. So if we have C, then we can find out what the angle is. And we need to get the angle first so that we can get the axis, because the angle shows up. So the axis, we could write it this way. And this is, if you're concerned about which frame is this in, maybe you don't remember, but from the last lecture, we said this E vector, it's got the same components in both frames. Those aren't little hats. Because when you rotate about a certain direction, that direction is the one direction that does not change, which means it has the same components in both. It has the same components in both the B and N. Once you've calculated phi, this is a 1/2 sine phi. And then these entries, it's C23 minus C32, C31 minus C13, and then C12 minus C21. So we'll calculate that for a particular choice. I'm going to see if there's a question here. Would C be the same regardless of the method you use? We're sort of starting from C as the basic thing. So I'm going to say yes. Maybe things will get clear as we go on. All right, so let's try this for an example. And I'm going to do the example from the book, but then I've also got one of my fancy little animations, do an actual numerical example. I'm actually going to fire up MATLAB and see if this works. So what we're going to do is say that the shuttle, the body fixed frame on the shuttle, has an attitude relative to an inertial frame given by the 3, 2, 1 Euler angles. That's yaw, pitch, and roll. Right, that is 10, 25, and -15 degrees. Although numerically, when I enter it, I usually use radians. C is the direction cosine matrix. It's that matrix that relates the B frame directions with the N frame directions. So yeah, same matrix. If you remember, how would we write that? So for these angles, it's given like that. So here, this is θ1, θ2, and θ3. I could try to write this matrix. Fortunately, there's code that in some sense comes with the book, but it's online. And it's a whole bunch of codes that go from all the different Euler angle sets to C, or from C to the Euler angle sets and other things. It also will go between other things. So I'm going to try to fire up MATLAB now, and we will see how this goes. So we're going to calculate the axis and angle. We'll first calculate the angle and then get the axis for this. Let's try that. What you're going to find is there is a rigid body. It's a zip file. And so this is provided by Hanspeter Schaub, who's the author of the book. You can get it from the AIAA website or his own website. He also has the same, I think, the same subroutines for other things like Mathematica and Python, but I'm only going to be doing demos with MATLAB. If you unzip this, it opens up something called MATLAB, and then it has all these files in it. The main one we'll care about right now, my goodness. So it's got all these Euler, and then it's got the convention, Euler 1, 2, 1 to C. That means it's going from the Euler 1, 2, 1. You will give it angles in the 1, 2, 1 convention, and then it'll produce the C matrix. What we want a yaw, pitch, and roll. So 3, 2, 1. Where is that? It's down here. 3, 2, 1 to C. And I think if I fire that up, it'll load it into MATLAB. And it's in some other screen, but here you can see what it does. So it takes in Q, which is an input vector of Euler angles. And it doesn't say it here, but they must be in radians. And then it's just calculating the components of the C matrix, just like I wrote in those lecture notes. So I'm already in this same folder that's got everything. I want to make, I guess I could do help Euler 3212C, and just to remind myself what this wants. Okay, returns the direction cosine matrix in terms of the 3, 2, 1 Euler angles. Okay, so this could be, I need to write it in terms of radians, and I think I said 10. So this will be times pi divided by 180. It's the first entry. Then 25 times pi divided by 180. Then what? Negative 15 times pi divided by 180. That'll just give me some numbers that are pretty meaningless to me. So now I'll just do cut and paste. Okay. Whoa, there it is, C matrix. I could do some things now like C transpose times C, and it's all ones. Yeah, but what about those negative signs? I don't know. C times C transpose. Some people like writing out the word transpose. You know, you don't have to. Just do C prime is the same thing. All right, so that's C. Let me clear the screen. That's C. All right, now let's get the principal rotation angle. And I don't know what to call that. I guess I'll call it capital Phi. The way that you do inverse cosine with MATLAB is ACOS. ACOS. And this was 0.5 times, and I could either write, you know, C11 plus C22 plus C33 minus 1. Okay, so that's in terms of radians. If we want to know, what's that in terms of degrees? Okay, 31 degrees. I have no insight as to why it's 31 degrees, but that's what it is. We're going to be just using these as coordinates to parameterize our matrix C, parameterize the rotation. Remember, this is an alternative to Euler angles. What about the E vector? This is 1 divided by 2 times sine of phi. Remember, phi is in radians, so good to go there. And now what? Times, now I do entries to a matrix. So this is C23 minus C32. I don't know if you know this little trick. If you want to go to another line, right, I'm going to be making a column vector, so I do semicolon dot dot dot. Go to the next line. C31 minus C13 semicolon dot 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 C12 minus C21. Now done. Oh, what did I do wrong? I'm missing an additional parentheses. You got to watch out with these parentheses. Okay, so that worked. Yay. So here's my vector. So it'll have those components. All right, great. So I'm going to turn off MATLAB for now and show you what this looks like. So let's try to remember what that was. So we calculated, we got that phi, at least in terms of degrees, is like 31.77 degrees. And E as a vector was something like negative 0.53, 0.74, 0.41. All right, that's cool. Let's try to interpret this. I've got an image. So this is showing the initial frame. Now I'm going to draw red on red. I don't know how reliably that's going to work. So this is N1. Straight down is N3. And this way is N2, because remember, we're using the convention that's typical for writing aircraft and spacecraft, which is that the B3 direction attached to the craft is down. So coming out of the nose here, this is B1. This is at the final configuration. So this is at that yaw pitch of roll of 10, 25, and negative 15 degrees. There's B1, B2, and then, you know, I don't know where B3 is, B3. Now, does this make sense? E is this vector over here that I've already drawn as orange. So there's E. And it's if you're wondering, where's it coming out of, like the origin somewhere. E is it's in the negative n1 direction. Yeah, that looks about right. Looks kind of like it's negative. It's got a positive n2 direction. Yeah, that seems about right. And it's got a less positive n3 direction. So again, that looks about right. So there's E. And there's going to be a rotation, and it's in the positive sense. So right-hand rule, I'm kind of going around like that through an angle phi, which is 31 degrees. So let's see an animation of it. I think this one just sort of gives you an idea of, if you're having a hard time viewing, what would a yaw, pitch, and roll of that amount do? This gives you an idea. And then there, orange is that axis. Okay. So let's see the rotation. Bzzz. How was it? See it again. Remember, so this is the gray thing sort of is showing the smooth rotation from one to the other about that. It's a pure rotation through an angle of 31 degrees about that orange axis. And there it is. So that's the sort of visual interpretation of what example 3.3 in the book is. Now, the book emphasizes there's another rotation angle, and I almost don't want to mention it because it's confusing. But right, to get to that, you could also go around the other way by an angle that's 360 degrees minus 31. The second angle one could use is phi prime equals phi minus 2 pi, or right, phi minus 360 degrees. So in this case, that would be negative 328.22. Right. You could rotate the exact opposite way through a larger angle, at least in terms of magnitude. You don't really want to do that. Typically want to stick with this smaller angle. What else is there? This is getting the angle and the axis from the direction cosine matrix C, but you could go the other way. You could say, well, if I have an axis and an angle, what is the C matrix? So to go from the axis and angle to C, we use that insight we had last time that we derived. These two get combined into something called the principal rotation vector. Right? Combine the axis and angle into a principal rotation vector. Again, that's terminology of Schaub Junkins and not necessarily everyone in the world. So they used the symbol gamma. They said, well, how about phi times E? So now we've got a vector. Right? Remember, E is a unit vector. But if we define this principal rotation vector gamma, then the magnitude of gamma gives the angle and direction gives the axis. And we sort of combine them into one 3 vector. And what we ended with last time is that you could write the matrix C is a matrix exponential, negative gamma tilde. Because gamma as a vector equals the angle phi times the axis, we could also write this as e to the negative phi e tilde. And just to remind you again what this tilde matrix does, eventually you'll remember it. This is negative E3 up there, E2, negative E1. And then I know it's anti-symmetric. So on the opposite side of the diagonal, I flip the sign. So that's weird. And matrix exponentials are indeed weird. What's the exponential of a matrix? You can only take the exponential of a square matrix. So A has to be square. So if A is, let's just say 3 by 3, but this works for any n by n square matrix. Then you first have the 3 by 3 identity. And then it looks exactly like the Taylor series expansion for e to the x, but you put in a matrix. 1 over 2 factorial a squared plus 1 over 3 factorial a to the cube plus 1 over 4 factorial a to the 4. It's an infinite series, just like it would be for a Taylor series expansion, infinite series. So what does this look like when we've got, in this case, a equals negative phi e tilde. So that's kind of odd. I'll write this as phi negative e tilde because I can. Then the C matrix is going to equal the identity plus phi negative e tilde plus 1 over 2 factorial phi squared. And the negatives cancel, and this just becomes phi tilde squared plus, and so on. Now, if you actually start collecting the terms, you'll notice a pattern. And this pattern was first found by a French mathematician named Rodrigues. So it's called the Rodrigues formula. And this is what it says. So this is the identity. First thing is the identity times cosine phi minus sine phi times e tilde plus 1 minus cosine phi times e hat transpose. So here we're thinking e hat is a column vector. So e hat times e hat transpose will give us a 3x3 matrix. And this is pretty cool. The book gives no fancy name to it other than equation 3.82. In the secret files of history, this is called the Rodrigues formula because Rodrigues was the first to notice this. When you carry out the Taylor series expansion, you notice things grouped nicely into sines and cosine. There it is. So this takes us from, this is going from the axis and angle to C. That's cool. So we could verify this numerically too. I'm going to use MATLAB again. If I can figure it out and get the parentheses to work with me. Yeah, so what I'll do is we'll just do example again from the book 3.4 numerically to verify that this works. I guess we could do it either way. We could either write the matrix exponential like we did up here, or collect terms like that and see if it works. I guess we could try both. Let's try this. Let's see our C matrix. Okay, that's C. I guess we could define gamma. Let's call it gam. Equals phi, has to be in radians, times E. Okay, good. Gam tilde. And now I'll just construct it. So this is 0, negative gam 3, gam 2. A little trick there. And unfortunately, it's not all lined up, but hopefully you get it. So this is going to be gam 3, 0, negative gam 1. And the last one was negative gam 2, gam 1, 0. Come on. Ooh, cool. Okay, now let's just sort of gam tilde transpose. Yeah, that looks right. I'll call the matrix I'm going to construct, I'll just write it as CC. And you don't just write EXP. The MATLAB syntax for doing a matrix exponential is EXPM. Just remember that. Negative gam tilde. Now compare with C. What? It works. Okay, so let's do C, C minus C. And it's, yeah, it's like machine precision difference. So it's good. Everything makes sense. We could try the Rodrigues formula. Maybe I'll call this CCC. I think it's I. Is it I? I, for whatever reason, I3. What is that? Yeah, the identity matrix. So I3 times cosine phi minus, oh, I haven't defined E tilde. Oh, no. But I can get it from gam tilde. Gam tilde divided by phi should be what I want. So I'll call that E tilde. Yeah, good enough. So CCC times cosine phi minus sine phi times E tilde. The last one's kind of weird. 1 minus cosine phi times E times E transpose. Why is it not letting me do that? Oh, I did something wrong. Parentheses. Okay, compare with C. Looks the same. Okay, C minus CCC. Yeah, machine precision. So that's a 10 to the negative 15. That's numerically a 0. Okay, so it all works. We checked it out. That's nice. Plus, you got a little tutorial on using MATLAB. Might be useful. All right, so we showed that this works, and that's good. Now, what I haven't mentioned is the kinematic differential equations. Just like we could have kinematic differential equations for the matrix C, which is 9 scalar ODEs, the kinematic differential equations in terms of Euler angles, which was 3 nonlinear ODEs, and had a singularity, meaning you couldn't use it everywhere, which is not good if we want to do control for something that could be arbitrarily oriented. We could write the kinematic differential equations for these. And I'm not going to derive them. You could look in the book if you want. I'll just give them to you. The kinematic differential equations for the axis angle. Think of these as 4 parameters that describe the orientation. And so we want to know, how do those 4 parameters change as omega changes? You have E instantaneous and phi instantaneous. As omega, the angular velocity viewed in the body fixed frame. So that's going to give us some, that word is time. That's going to give us some differential equations. So those differential equations are these. Phi dot equals E transpose times omega, where omega is written in terms of body fixed frame. And then E hat dot, that's equal to 1/2. And this is going to be a matrix. E tilde minus cotangent. Cotangent has not yet made an appearance. Of phi over 2 times E tilde squared. So you just take the matrix times itself. And then that's all times omega. So these are 4 ODEs. They are better than Euler angles, but they still have a problem. And I don't know if you can see the problem, but there is a problem with this set of parameters. The problem is when you've got no rotation. When you've got no rotation, that means phi equals 0. The axis could be anything. The axis could be in any direction. It's like I'm rotating 0 degrees about any direction. And so that's a big problem, especially if you want to design some controller that controls about a particular direction and you don't want to move. You don't want to have a singularity at the no moving point. So this becomes a problem. That manifests itself here. At phi equals 0, this will give problems. So we can't use this everywhere. So we still have a singularity, meaning the orientation, the attitude corresponding to not changing, so no rotation at all, is the singularity here. So in some sense, you might say, well, this is actually worse than Euler angles. I see no advantage. Well, you have a point. Still have a singularity, which is not good when doing attitude control. And by not good, I mean millions of dollars will be lost and the mission will fail. But there's hope. There are other parameters that do not have a singularity, and they come to the rescue and they save the day. There is hope. These are the Euler parameters. Euler's name is just getting thrown around like everything. The Euler parameters, which are the elements of the quaternion. So we might say we're talking about quaternions, but we'll use the terminology of the book. The Euler parameters are the individual elements of this thing, and this is in section 3.5. The Euler parameters they're popular because they do not have a singularity, meaning you could describe any orientation with them. We could define an Euler parameter vector. The Euler parameter vector beta has elements, and the first element's called beta naught, and then beta 1, beta 2, beta 3. So this may differ from how other books describe quaternions. Sometimes quaternions do it differently, but anyway, this is how the book does it, and that's what we're going to follow. And the way they're defined is beta naught is cosine of phi divided by 2, and then beta 1, beta 2, beta 3 are just E1, E2, E3, and times sine phi over 2, all of these. So that's how they're defined. This is equation 3.96. And because the axis is a unit direction, so E1 squared plus E2 squared plus E3 squared equals 1, right? This is what E dotted with E hat dotted with E hat equals 1, because it's a unit direction. So we get that. Because of that, the norm of the Euler parameter vector is equal to 1. So the norm of this Euler parameter vector, let's do the norm squared, beta naught squared plus beta 1 squared plus beta 2 squared plus beta 3 squared. What do we end up with? We get cosine squared of an angle plus sine squared of that same angle. And so that equals 1. So that this can become a numerical check when you come up with the kinematic differential equations for beta. So this is how beta is related to, in some sense, what we've written here is going from the axis angle to beta. That's sort of where they came from. You could also go from C, the direction cosine matrix, to beta. And that's equation 3.99. And we could go from, from beta to C. By go, I mean transform. And if you want to see what that looks like, it is, it's not pretty. There it is. You do not have to write this down. It's this is equation 3.98. It's also in the code, the MATLAB code. I think it's called C2EP.m. It's C, transforming from C to the Euler parameter. Takes you, I guess that's the one up here, isn't it? So C2EP.m. And I'm guessing there's an EP to C.m. So if you want to, we could take that same matrix in MATLAB and see what it looks like, just for funsies. And you could do it by hand, or like I said, use that code. So may as well use the code. Somebody's already done this. And so this is, I'll do help C2EP. Yes. Okay, great. Actually, instead of writing it as Q, I'll write it as beta. Beta equals C to EP C. There it is. So it went through the calculation, and I'm just, is there an EP to C? I hope. Oh, what do you know? Okay, EP, I'll call this CCCC. You see how excellent my coding skills are. Beta, how does that compare? C minus CCC. It's about the same. It is the same. It's the same. Good. Yay. And I think somehow this is the same as the calculation in example 3.6. Tells you how to do this. I think the thing that we'll end with is the kinematic differential equation for the Euler parameters. So we just did that example, example 3.6. Yay. The kinematic differential equation for the Euler parameters. They're written different ways, right? And this is, how they change. So it gives you how beta changes in time from omega changing in time. There's different ways to write it. One way that it's written that looks kind of nice. I'll write it this way. Beta dot, remember this is a four-dimensional ODE, 1/2, and now this B matrix as a function of beta times omega, the angular velocity vector written in the body fixed frame, where B beta, this is a 4x3 matrix, right? Because omega is 3-dimensional and beta is 4-dimensional. Right? This is just shorthand for beta not dot, beta 1 dot, beta 2 dot, beta 3 dot. And this is following along in the book. This is, it's not particularly enlightening. It's just a bunch of betas. Beta not, negative beta 3. Like I don't know how to remember this. Just gotta look it up. Beta 2, beta 1, and this is beta not again. So there, and this is 3, 1, 1, 2. There's no singularities. So that's the advantage here. These ODEs have no singularities, which means they're a convenient set of parameters for describing arbitrary rotations, which will be really useful when we get to rigid body dynamics and including control. So now let me show you that there's going to be a homework 4 assigned soon. So I haven't posted it yet. The description of the problems fits on one page. So that's pretty amazing. This is the first, it's 3 problems. Again, only turn in a single PDF. I want you to go through the exercise of doing what I did for the 3-2-1 Euler angles, but do it for the 3-1-3. So that means write the rotation matrix C in terms of the Euler angles, theta 1, theta 2, theta 3, like we did in class. And then same thing for the kinematic differential equations for the 3-1-3 Euler angles. And then finally, what is the geometric condition for which these equations will encounter a mathematical singularity? And then, of course, to check your answers, the answers are in Appendix B of the book. And then what we did today was something a lot like problem 2. So the axis angle variables and Euler parameters. You could use a numerical software package like MATLAB. So it's, from a yaw, pitch, and roll angle, you'll get the cosine matrix. It's okay with me if you use the code that's provided for all of these. I think for the numerically verifying, you might not be able to do that, like maybe not for this one. I don't know. And then that equation 3.98 using the Euler parameters. The last one, so we'll talk more about that next week, but this is numerical integration of those beta parameters. So you're told you have an initial yaw, pitch, and roll of this. So translate that initial attitude. So you'll construct a C matrix, and then from the C matrix, turn this into an initial So beta at an initial time. And then you need to simulate this and how it changes with this given as your omega. So instead of solving for how omega changes with time according to rigid body dynamics, you're just sort of given, hey, here's an example. And here in t, this t should be in seconds. And you're given this in terms of 20 degrees per second. But everything has to be written in terms of radians to get things correct. And then you'll plot the 4 Euler angle parameter histories. So they'll be like, beta naught as a function of time from 0 to 60 seconds. And I don't know what it'll do. But the magnitude squared, which is this down here, should be numerically very, very close to 1. All right. So that's a kind of brief run through with the homework. I see some questions in the chat, so let me answer that. Plus, I think you're unmuted too, but let me answer these. Some of these KDEs are not often solved. Is this one often solved? Yes, because it doesn't have a singularity. So that's why for practice, you will solve it. Okay, I'm signing off. All right, bye.